Hi, I'm Paul Kyogan from GK Tuition, and in this video I want to talk to you about inferential statistics. Now the question that I've chosen to go through here is 2017 Paper 2 Question 8 Part A. In this question we're told that the weight of 15-year-olds in a country is normally distributed and that the average weight is 63.5 kilos. So you have a situation something like this. We're told that the standard deviation of this population is 10. And then we're introduced to Mariska. Mariska weighs 50 kilos. And we're asked to work out the percentage of 15-year-olds in that country who weigh more than Mariska. So I think graphs really help with understanding in these questions. The average is 63.5. Clearly Mariska will be to the left of the mean or below the mean because she only weighs 50 kilos. Now the question is to find the percentage of 15-year-olds in this country who weigh more than Mariska. Or in other words, what percentage of this normal curve will be above 50? In order to do this, you need to convert Mariska's sample into a z-score. To do that, you use your standardizing formula from your log tables. To convert Mariska's z-score into Mariska's sample into a z-score, my x in this case, my sample is 50, the population mean is 63.5, and I'm going to divide by the standard deviation. In other words, I'm basically comparing the strangeness of 50 within this normal curve. I'm comparing 50 to the average, dividing by the variation or the standard deviation. So in this case, her z-score works out as minus 1.35. So instead of using this practical normal curve, what you should actually use is this normal curve. This is the normal curve from our log tables, and I know Mariska's z-score is minus 1.35. And in fact, the question is to find the percentage of figures in any normal curve that have a z-score larger than minus 1.35. So to work that out, you should write it as, that's the probability that z is greater than or equal to minus 1.35. Now, you cannot read a negative z-score off your log tables, so in order to get rid of a negative z-score, you have to change the inequality so it becomes less than, and you also change the sign of your z-score. Greater than minus 1.35 is the same as less than plus 1.35. Now you can read this straight off your log tables. The probability that z is less than 1.35, less than or equal to 1.35. If you go to your log tables to your z-score of 1.35, it tells you that the proportion of a normal curve that are less than 1.35 is 0.9115. Now, if I want to leave that as a percentage, I multiply it by 100. My final answer is 91.15%. So 91.15% of 15-year-olds in this country will weigh more than 50 kilos, more than Mariska. In A part 2 of this question, I want you to notice that it is the exact opposite of A part 1. In A part 1, they told me Mariska's weight, and they asked me to find the percentage of 15-year-olds who weigh more than Mariska. In A part 2, they've told me the percentage of 15-year-olds who weigh more than Kamal, and they've asked me to find his weight. So it's the exact opposite. I'm going to be working backwards. They told me that Kamal, 1.5% of 15-year-olds weigh more than Kamal, and they've asked me to find his weight. So it's they said it's the same country, which means the standard deviation and the mu stay the same. I know that 1.5% of 15-year-olds weigh more than Kamal. As a decimal, I can represent that as 0.015. So the proportion of figures to the right of Kamal is 0.015. By extension, that means that 98.5% of 15-year-olds weigh less than Kamal. And I can represent that as 0.985. So I know that the proportion of figures less than Kamal's weight is 0.985. Now if you go to your log tables on page 35 and page 36, you need to look within the middle of your table and find, this is your proportion, you need to find what is the corresponding z-score. So you're using those tables probably the opposite way that we usually use it. If you find the figure 0.985, you'll realize that that corresponds to a z-score of 2.17. So now I know that if 98.5% of 15-year-olds weigh less than Kamal, he must have a z-score of 2.17. So now I know sigma, I know my population mean, and I know my z-score. If you know sigma, your population mean, and your z-score, we can now use the standardizing formula in order to find x, which in this case, x will represent Kamal's weight. So if we just sub in, we'll get 2.17 is equal to Kamal's weight minus 63.5 over 10. In order to get rid of my fraction, I would multiply both sides by 10, and I get 21.7 is equal to x minus 63.5. In order to get x on its own, I would add 63.5 to both sides, and you end up with 85.2. So you know that if 98% of 15-year-olds weigh less than Kamal, based on this normal curve, Kamal must weigh 85.2 kilos. Okay, so now we need to talk about A part 3 of this question. In A part 3 of this question, I want you to put yourself in the shoes of the researcher, okay? It's now 2016, it's a year later, and they want to figure out, has the average weight of 15-year-olds changed from 2015 to 2016? Now, it would be impractical. Obviously, in an ideal world, they would weigh every 15-year-old in the country. But maybe there's 10 million 15-year-olds living in this country. It's probably completely impractical to weigh all of them. So as a researcher, all you could do is take a sample of maybe 150 15-year-olds, and you could weigh them. So that's what they've done in this case. They took a sample of 150 15-year-olds, and the average of the 15-year-olds they weighed was 62 kilos. Now, just because, so it's 1.5 less than it was last year. But that doesn't necessarily mean that the average weight of 15-year-olds in the whole country has changed. It could be a coincidence. It could be a fact that just the 150 15-year-olds that the researcher weighed just happened to be below the average. So in a hypothesis test, we need to measure this. We need to figure out, is there a statistically significant difference between the 62, the result of your sample, and the 63, which is the population mean? Is it a statistically significant difference, or is it just a coincidence? Which it very well could be. And in order to do that, we need to do our calculations here, but I'm going to talk about that in a second. The first set of marks go for our null hypothesis and our alternative hypothesis. You always work off the assumption that there is no statistically significant difference between the X bar and the population mean. That it's just a coincidence that the people I weighed happen to be 1.5 kilos less than the average. And to write that, I would say that the mean weight, the null hypothesis is that the mean weight has not changed from 2015 to 2016. Alternatively, the alternative hypothesis is that the mean weight has changed from 2015 to 2016. Mathematically, what this one means is I don't think there's any statistically significant difference between these two. It's just a coincidence. Whereas this one means that actually that's a big difference between them. It's hardly a coincidence. The average weight of 15-year-olds must have changed. Now, in order to, so basically I need to compare my X bar to my population mean. And in order to do that, you want to use this formula. Basically, you want to convert it into a Z-score. So it's your sample mean, the result of your sample minus the population mean, divided by the standard error, divided by sigma over the square root of n. So in this case, I'm comparing the result of my sample to the population mean, dividing it by, say, the variability. You can think of it like that. And in that case, your Z-score works out as minus 1.8371. Now, a lot of students lose marks on their conclusions for this one. I want you to go to conclude these questions by 3 different methods, and I'm going to do that on the next slide. In order to conclude these questions, I think you should do it by 3 different methods. The first thing you should do is a graphical representation of what's going on. You sketch your normal curve, you mark in 1.96 and minus 1.96. If your Z-score had worked out within this region, you would fail to reject HO. If your Z-score worked out bigger than 1.96, you would reject HO. If it was less than minus 1.96, you would reject HO. And then you mark in your Z-score. So in this case, I've marked it in here. It's roughly somewhere there. Our Z-score worked out as minus 1.8371. So graphically, that shows your examiner that you know what's going on. To explain this in terms of an inequality or mathematically, you could say that, right, well, in this case, Z is between minus 1.96 and 1.96, so therefore I'm going to fail to reject HO. If you're failing to reject HO, you can stipulate that there's a 95% chance the mean weight of 15-year-olds has not changed. So you just reiterate what your null hypothesis was in the first place. Now, I hope this video made sense. If there's anything there you're unsure of, then just don't hesitate to email me or ask me in class, and I'll try and clarify it for you.